What is the ocean's heat budget? So, it's the net balance of oceanic heat gains and losses from different fluxes. Welcome to the crash course. So straight into it, the first component we're going to be looking at is the radiative flux, where QS and QB are the solar incident short waves and surface emitted long waves respectively. This flux depends on the emissivity of the body and the temperature to the power of 4. On to advection. So this is a net heat transfer between adjacent water masses, i.e. advective, upwelling, sinking, or mixing processes, and this is a mechanical mode of transfer. It can be net positive or negative, but over the whole ocean, it's zero. Change of state processes denote heat exchange via latency, i.e. when water converts to a more excited gaseous state, energy is removed locally to enable the transition, with condensing in the atmosphere providing local latent heat to be radiated back to the ocean surface. Conduction here refers to the net amount of heat transferred to the atmosphere via thermal transfer across the air-sea interface. This is prominent for a steady, motionless ocean, but in reality this transfer of heat is dominated by turbulent flow. More on this later. This flux term refers to the surplus or deficit of total heat, i.e. the leftover net flux that is available to increase or decrease the ocean surface temperature. Now we can delve into some more detail about the nuance of each individual term. Looking back at our balance of solar insolation and surface emittance that describes the net radiative flux, it's worth mentioning that these quantities are strongly affected by climate feedback such as clouds, and while they do have reflective or cooling effects, they also re-radiate long-wave radiation back to the ocean surface. The radiative transfer itself can be described via this equation, so this is your shortwave and long-wave flux per unit area that depends on the emissivity and surface temperatures of the respective emitting bodies, where sigma is the Stefan Boltzmann constant. Through Wien's law, we can also relate the temperature of the body to an approximate black body behavior to acquire a definition of the wavelength of electromagnetic radiation for which the body will be most strongly absorbing. Another strong player in the climate game is sea ice, which has multiple functions that we are interested in for the sake of this video. Similarly to clouds, it is also part of a reflective albedo feedback, which is positive with global warming. Also insulating the ocean, i.e. reducing temperature gradients adjacent to the ocean surface. It inhibits momentum transfer between atmospheric winds and the ocean surface, and this is dependent on multiple factors such as ice surface roughness, concentrations, and surface stratification. Something significant regarding sea ice is the formation of leads. These big cracks in the ice, why are they important? Particularly in the winter when the local atmosphere is so much colder than the ocean surface, there are very strong temperature gradients between open ocean water and the air. This transfer will mainly occur via conventional conduction, and due to such large gradients, can occur in the orders of hundreds of watts per meter squared. Conduction will be occurring via this process, where QH is the conductive flux and is equal to the thermal conductivity of the medium multiplied by the temperature gradient. The temperature gradient is negative if going from higher to lower values, which is the most feasible case for ocean to atmosphere since the ocean is going to be warmer. Typically, if we're not in polar waters, this flux is only really occurring over centimeter scales, and hence this thermal transfer is governed by atmospheric-induced turbulence, where we associate higher turbulence with higher energy fluxes. This flux is a function of density, specific heat capacity, fluctuating vertical wind W, and fluctuation potential temperature theta. The brackets denote an hourly or so temporal average, followed by a bulk parametrization definition with dependence on temperature difference, transfer coefficient for sensible heat CH, and scalar wind speed S relative to the ocean surface. And now we can bring in a surface wind stress term tau, and this is a momentum flux at the air-ocean interface. It depends on UVW, i.e. the X, Y, Z components of the wind, specific humidity, and CD, which is the transfer coefficient for momentum, otherwise known as the drag coefficient. This term itself has some dependencies, namely ocean surface roughness and atmospheric stability. The first definition here is the drag coefficient, and it holds familiar terms. The second definition is a parametrization that includes a roughness length Z0 and a function psi that accounts for stability. Officially revisiting our evaporative and condensation term, our latent transfer term, we see a latent flux that is proportional to the rate of change of mass that is changing state according to, in this case, the latent heat of evaporation from the surface ocean. So leading from this, we can imagine per molecule in an energy potential scenario, this is the energy required to bring it to infinity and break the bonds, allowing the water into a gaseous state. So imagine a unit volume of water. We know that the net flux that is available, Qt, to change its temperature is the sum of all the different fluxes, being radiative, Qs and Qb, shortwave and longwave, Qe, the evaporation and condensation output and input respectively, QH, the conductive and turbulent contributions, and QV, the advective term, which we qualitatively touched on as well. Thanks for joining.